There is a number that gets repeated constantly in conversations about Mars. 7 months, 6 to 9 months, about half a year. People say it confidently, as if the trip were roughly as predictable as a flight across an ocean. Longer, obviously, but the same kind of thing. A fixed journey with a known duration. That framing misses almost everything interesting about the problem. 7 months is not wrong, but it is the answer to a question most people have not actually asked. The real question, why 7 months, what determines that number, and why we cannot simply go faster, turns out to be one of the more elegant pieces of physics in all of spaceflight. Understanding it does not just tell you how long the trip takes. It tells you something about how the solar system is structured and why navigating it requires thinking in a way that is genuinely counterintuitive. Start with the distance because most people's intuition here is off by a significant margin. Mars is not at a fixed distance from Earth. Both planets orbit the Sun, but they do so at different speeds and on different tracks. Earth, closer to the Sun and moving faster, completes one orbit in 365 days. Mars, farther out and slower, takes about 687 days to complete the same circuit. Because they are moving at different speeds on different paths, the distance between them is constantly changing. When Earth and Mars sit on opposite sides of the Sun, the separation can exceed 400 million kilometers. When they align on the same side, a configuration called opposition, that distance compresses to as little as 54 million kilometers. The ratio between those two extremes is roughly 8 to 1. Mars can be 8 times farther away, depending on where the two planets happen to be in their respective orbits. So the first honest answer to how long the trip takes is, it depends on when you leave. But the more important answer is that even the minimum distance, 54 million kilometers at closest approach, does not tell you how far the spacecraft actually travels. And that gap, between the straight-line distance and the actual path, is where most of the explanation lives. The reason you cannot simply aim a rocket at Mars and fire is that by the time the spacecraft covers even a fraction of that distance, Mars has moved. Planets do not wait. A spacecraft launched directly toward Mars's current position would arrive at empty space. The place where Mars was, not the place where Mars is. At the speeds spacecraft travel, the transit takes months. Mars covers an enormous arc of its orbit in months. The two facts together make a direct trajectory essentially useless. The solution is to stop chasing the planet and start thinking in orbits. Every spacecraft launched toward Mars does not travel in a straight line between 2 points. It enters a new orbit around the Sun, an elongated ellipse that begins at Earth's orbital distance and ends at Mars's orbital distance. The spacecraft follows this ellipse passively, coasting through space under the Sun's gravity, until it arrives at the far end of the arc at the exact moment Mars arrives at the same point from a different direction. The two meet in space not because the spacecraft chased the planet, but because both followed their own orbital paths to the same location at the same time. This technique is called a Hohmann transfer, named after the German engineer Walter Hohmann, who described it mathematically in 1925, decades before anyone had the rocket capable of attempting it. It is the most fuel-efficient route between two orbits in the solar system. Not the fastest, the most efficient. That distinction is everything. Because the spacecraft is following a half-ellipse rather than a straight line, the actual distance covered is considerably larger than the gap between the planets at launch. Depending on the specific alignment, a Mars mission following a Hohmann transfer typically travels somewhere between 400 and 600 million kilometers, even when the straight-line distance between the planets at departure is a fraction of that. The path curves through space in a long, graceful arc. There are no shortcuts. The mission record makes this concrete. Mariner 4, launched in 1964, took 228 days. Mariner 6 in 1969 took 156 days. The Mars Global Surveyor, launched in 1996, took about 300 days. The Mars Science Laboratory, the spacecraft that delivered the Curiosity rover, launched in 2011 and traveled for 254 days. The Perseverance rover's spacecraft, which landed in February 2021, made the journey in 203 days. The variation across those missions reflects differences in launch alignment, spacecraft mass, and trajectory design. What they share is a consistent range, roughly 6 to 9 months, clustered around an average of about 7. That range is not a coincidence or an engineering limitation that will be solved with better rockets. It is the natural timescale of the Hohmann transfer between Earth's and Mars's orbits. It is what the geometry of the solar system produces when you optimize for fuel efficiency with chemical propulsion. There is one more constraint that shapes all of this, and it is the least intuitive piece of the problem. You cannot launch toward Mars at any time. The Hohmann transfer only works when Earth and Mars are positioned in a specific geometric relationship, with Earth slightly behind Mars in the race around the Sun, so that by the time the spacecraft reaches Mars's orbital distance, Mars has traveled exactly far enough along its path to be at that meeting point. This alignment, called a launch window, occurs roughly every 26 months. Miss it, and the next opportunity does not arrive for over 2 years. The window is not generous. The geometry has to be right to within days. Launch a week early and the spacecraft arrives ahead of Mars. Launch a week late and it arrives behind. Space agencies plan Mars missions years in advance, specifically around these windows, and the launch schedule for every Mars mission in history reflects them. This is why the question of how long it takes to reach Mars cannot be answered with a number alone. The number comes from the intersection of orbital geometry, fuel economics, and a 26-month scheduling constraint that the solar system imposes regardless of what we prefer. 7 months is not the time it takes to cross a distance. It is the time it takes to follow the most efficient orbital path between two moving targets, launched during the narrow window when that path is available. Now, the obvious question, could we go faster? Yes, in principle. A spacecraft could be given significantly more initial velocity, pushed harder off Earth so that it follows a shorter, more aggressive arc rather than the gentle Hohmann ellipse. This would reduce transit time. Some trajectory designs for crewed missions, which prioritize reducing radiation exposure during the transit, have proposed trips as short as 3 to 4 months using high-thrust propulsion concepts like nuclear thermal engines. The cost is fuel, and the fuel cost scales in a way that becomes prohibitive quickly. In spaceflight, velocity changes do not cost fuel linearly. The relationship is exponential. Doubling the transit speed does not double the fuel requirement. It multiplies it by a factor that rapidly overwhelms the carrying capacity of any rocket we know how to build. Every kilogram of propellant added to go faster must itself be accelerated, which requires more propellant, which must itself be accelerated. The compounding runs in the wrong direction. This is why the Hohmann transfer has remained the standard approach for Mars missions across 6 decades of spaceflight. Not because engineers lack ambition, but because the physics of the rocket equation makes efficiency the only viable strategy with chemical propulsion. The 7-month figure is not an artifact of limited technology that will disappear with better engineering. It is the timescale that the solar system's geometry and the rocket equation converge on when you operate within the constraints that currently define spaceflight. What would actually change the number is a different class of propulsion entirely. Nuclear thermal propulsion, using a fission reactor to heat propellant rather than chemical combustion, could plausibly reduce Mars transit times to 3 or 4 months at equivalent payload. Ion propulsion systems, which produce very low thrust continuously over long periods, can be more efficient still on the right mission profiles, though they introduce their own trajectory complications. Neither technology is currently flight-ready for crewed missions. Both are under active development. Until one of them reaches operational maturity, the answer remains what it has been since Mariner 4 in 1964. With current technology, reaching Mars takes approximately 6 to 9 months. The specific number within that range depends on the alignment at launch, the design of the trajectory, and the performance of the spacecraft. The average across historical missions sits close to 7 months. That figure deserves some respect. It is not a failure of imagination or a gap in ambition. It is the result of following the most elegant available solution to a genuinely hard problem, moving a spacecraft from one orbit to another across hundreds of millions of kilometers, without missing, without running out of fuel, and arriving at a planet that has been moving the entire time. The day that number drops to weeks rather than months will represent one of the genuine turning points in the history of spaceflight. Not because the destination changes, but because the relationship between Earth and Mars does. A 7-month transit makes Mars a remote outpost. A 3-week transit makes it a neighbor. That transition is possible. It is not imminent. And understanding exactly why the journey currently takes as long as it does is the clearest way to understand what would have to change to make it shorter.